I'm going to introduce Dr. Max Perez and do a real quick introduction, and then Max, we can maybe have the rest of the panelists introduce themselves if they like, or you can introduce them. So Dr. Perez is the Vice President of Strategic Initiatives at Infleqtion, which is formerly known as Cold Quanta. Infleqtion is based on 15 years of pioneering quantum research. Its scalable and versatile quantum technology is used by organizations around the globe and is deployed by NASA on the International Space Station. All right, Max, I'm going to hand it off to you. You can use that microphone if you'd like. Until you guys are ready. You're ready.
Whatever. Ready for karaoke.
Good afternoon, everybody. Thanks for joining us for the post-lunch session. We had a little bit of a go-around to understand where our commonalities and differences are at this point, and I think we have more commonalities and differences, but I'm going to go ahead and let the other panelists introduce themselves in a second. As was mentioned, I'm from Infleqtion. Infleqtion has has activities along all three technology verticals in quantum, but sensors are near and dear to my heart. I came from a sensors world back well before it was even called quantum, back when it was just called atomic technologies. So it will be a lot of fun to dig pretty deep into what's going on with quantum sensors today. Nick?
Hi, everybody. My name is Nick Werstiuk. I'm CEO of Quantum Valley Ideas Lab in Waterloo. We're a not-for-profit independent research lab focused on quantum sensing. We do TRL 3 to 6, 7 idea to commercial-ready prototype, and then create companies to take those technologies into specific products, into specific markets. My background is 25 years, of product management, commercializing new technology. So I'll hopefully provide that spin or perspective on this discussion.
Thank you. I'm Bonnie Marlow. I lead the quantum sensing group at the MITRE Corporation, which is a not-for-profit organization that operates 6 federally funded research and development centers, or FFRDCs. So we do kind of a mix of different types of work at MITRE. We do a little bit of basic and early applied research, and then we also do a lot of sort of strategy development and analyses in support of various government sponsors, thinking about how to help mature quantum sensing technologies for those applications that we think will be the most useful.
And I'm the last one. My name is Jeff Buchsbaum. I'm from the National Cancer Institute, and I'm representing the NIH, or HHS, so government. We have a working group at the NIH, and there'll be a slide later. I thought I had a much longer amount of time than I will have, so the slides will be super short, I promise. But yeah, we try to fund things and help people doing science. I particularly am a pediatric radiation oncologist, so I look at translating quantum sensing and quantum computing to curing cancer.
So to kick it off, we had an email thread that went around to kind of identify the things that we have in common. I noticed at least 3 of the 4 of us have pretty solid activities in what's known as quantum RF or Rydberg-based sensing. So this is a really exciting new technology in RF sensing and or receiving. It's been getting a lot of press lately. Maybe I'll kick it over to Bonnie to talk a little bit about what are the advantages of that particular flavor of quantum sensing?
Sure. Yeah. So I think these sensors really have a fundamentally different principle of operation than traditional antenna-based receivers. So they have some unique properties. I think early on there was this hope that they were going to be extraordinarily sensitive, and at the moment they're okay. But I think there's a long road ahead of them in terms of, being competitive with the antennas in terms of sensitivity. But for a lot of applications, you don't necessarily need more sensitivity. What you might need is, a completely different sensing modality that could enable other unique applications. So one interesting thing about the Rydberg sensors is that they have extremely wide band tunability. theoretically, I think there have been measurements from 30 hertz up through 630 something terahertz, or gigahertz, so close to terahertz. And you just can't get that with a single antenna-based receiver system. In addition, they don't they don't generate. They're actually non-absorbing and non-reradiating, and so they don't, if you bring them very close to metallic structures like antennas, they don't generate mutual inductive coupling. So that can help with, very near field metrology, or in sort of the DoD language, we would call it, they might be able to help with co-site mitigation. So being able to have, kind of a receiver that you can put very close to other spectrum equipment that's always operating, but that won't be generating noise or interference with that other spectrum equipment. Maybe I don't know if Nick wants to add anything.
Sure, I'm gonna build on that. So those two scenarios that Bonnie talked a bit about, right? So one of the areas that we see a lot of potential is exploiting some of those non-pure sensitivity functions, right, and applying them to markets where that's valuable, right? So one market is actually the plain old vanilla test and measurement market for RF devices, right? There are advantages in that technology, both for device testing for wireless devices. We think there's use cases in base station testing, right? So any 5G telco could be an end user of this technology. And we also think there's usage in manufacturing production of RFICs, right? So testing on the product line. So I think there's scenarios there that sort of push, that may not require ultimate sensitivity, but add value in markets that are fairly large and substantial. And the high frequency response, the sensors are really nice because they're not proportional to wavelength. You don't have a 30-meter antenna. You have a 2-millimeter square vapor cell sensor that can be used for a range of frequencies. The other side is maybe we're tilting at windmills, but we are trying to tackle the sensitivity problem with some innovation in the sensor head to try and push the boundaries of the technology towards sensitivity that's on par with current classical electronics receivers, right? So we do think there's an eventual use case here, potentially in radar or high performance communications use cases as well. So we'll see where that comes out, but that's definitely an area of interest as well.
And you just spun out a commercial company in this space, right? From Quantum Valley. Can I ask what the focus is there? Where do you see commercial advantage?
Sure. So we did it by project. So the first project is a test and measurement product company, right? So we look at developing the technology. We've developed about 40 patents in this technology over the last 5 years. And so our goal with that is to basically then create a company that'll be laser focused on producing a product that solves market use cases, right? So they have an MVP, we have a prototype that's essentially the MVP, and essentially they're gonna build from that and then take that to market in flavors of test and measurement. I'm not sure exactly where they're gonna go first, but you can expect sort of that's kind of the direction that we're headed in terms of capability and performance.
And Jeff, where do you see advantage for Quantum?
The interesting segue. So to both of the two first speakers, so I'm a computational physicist and have a background in some of this material. We just put out a PAR, or whatever, an SPR announcement for quantum sensing funding support. And for small companies, which is defined as greater than, I think, 50% US owned, less than 500 employees, phase 1 of these grants is $400,000 a year, and phase 2 for the second and third year, if you get to phase 2, is $2 million. And it's to do quantum-based questions for biological things. And so we also put a contract topic at the NCI out for biological sensors. There's no reason why you can't do a quantum biological sensors, so these would be implantable things. The idea being that the quantum sensors can give you a sense of what's going on with a patient or a person while they're being treated in a much less invasive, much less toxic way. Examples of this, for example, to answer your question, when we talk to people at the International Space Station, which is technically a national lab, it's not actually NASA, they are doing all sorts of interesting things in low gravity to mimic aging, and quantum sensors in that context will allow tissue samples to be studied for longer periods of time before the light of, say, a light microscope blanches out and damages the tissue. So you can study what's happening with a quantum sensor for longer periods of time. We have very limited biosamples. If you have cancer, your family has cancer, you want to find out what's going on, those samples from other people that have had cancer are incredibly valuable. You can't just go sticking needles in people. People don't like that. So quantum sensors that can use much smaller sample sizes can make those kinds of biorepositories converting them, they can convert them from finite resources for the country or the world to infinite resources if very small sample sizes are needed for the same science. Those are just some examples, but we are a grant funding place, and our goal is to help all of you be successful, and we fund you. So you just have to put in grants or applications.
Thank you. So one of the other areas that overlaps both biomedical and other modalities of quantum sensing is in magnetometry. This is one of the success stories over the last 10 years is the leveraging of what was originally a clock technology for compact magnetometry use, at least at a NIST, and from other origins. Maybe I'll pass it over to Bonnie to see if there are any of these technologies that have found uses in multiple arenas using the same core technology. So I know magnetometry was used originally for imaging of the magnetic fields off of the brain and the heart of human bodies, but it could also be used for navigation, and it could also be used for mineral discovery. Any other multi-use technologies you see coming out of quantum today?
Yeah, I mean, I'll add to those and say, magnetometers, as you said, I think are nice in that they're multi-use. I think the atomic and superconducting based magnetometers can achieve really exquisite sensitivities, and that's really important for biomedical imaging and sensing. But then for magnetic field aided navigation, which is, sort of a hot topic right now in that there's, in general, this broad interest in figuring out, if we ever lose access to GPS or the GPS signal is just degraded for an extended period of time for whatever reason, how can we ensure that we can continue to navigate and communicate in a reliable way? And so magnetic field-aided navigation is a relatively promising technique for position fixing. And that is one of those applications for which I would argue that we're going to need quantum sensors. At the very least, we'll need them for generating really high accuracy magnetic maps to use as the reference for magnetic anomaly-aided navigation. And that's actually not due to their sensitivity. We actually don't need to leverage the exquisite sensitivity of atomic magnetometers to do that. The background magnetic noise is too high. We don't really need the best sensitivity for that. But what we need is the extremely good long-term stability that's offered by atomic magnetometers. You can't really get that same level of reliability with classical flux gate magnetometers.
I don't have as much direct familiarity with the magnetometer space. We don't have actual research in that area. I have seen, I think, this interest in applying those technologies. I think I will build on Bonnie's point, though, right, that sensitivity, as we said earlier, isn't the end-all, the be-all. And some of these things around stability or potentially, if you're looking at inertial navigation, calibration and setup time, right? If you can do away with 20 minutes of driving around in a circle, basically calibrating your inertial measurement unit and do that automatically with a quantum device, that's suddenly a significant user impact in the field, right? And that's some feedback we've had as we've talked to both aviation and marine navigation companies that we're working with to look at some of those use cases and see where the technology might fit.
Yeah, so thank you for the segue. So it's a big deal. The magnetometers in quantum are really game-changing. Magnetometers for encephalography or brain studies change these Dr. Evil kind of James Bondy monster machines that are really uncomfortable to be in or around into these little bicycle helmets that kids can walk around in if they have medical problems. It democratizes the availability of the technology. More to the point, when I was a grad student, we had to do NMR with these big many million dollar 700, 800, 900 megahertz machines. Now they're benchtop. That's going to completely change the availability of structural biology, which directly impacts drug discovery. So everyone can do the kinds of things that only a major university could do much more affordably. And I could go on and on and on. It's literally game changing.
Yeah, please.
So that triggers a comment, right? And I think it builds on what your Infleqtion CEO said to her earlier about manufacturability. So think about those meg helmets, right, having 400 optically pumped magnetometers in them, right? If it takes a artisanal PhD student a day to make one of those, you get one helmet a year, right? So that sort of speaks to the scaling problem that I think the quantum sensing industry has to face. And I do agree with what your CEO said earlier, that that's a real big challenge of trying to make these solutions and use cases usable for people, right? So if every hospital wants one of those, then your P times Q is significant, right? And you need to be able to support that P times Q with a volume production capability.
So maybe I'll ask Bonnie if she can extend on the manufacturability of these systems. So one of the great things about magnetometers is that photonically they're relatively simple, but the core element, the place where the atoms actually live, has to be scaled up in production, and that's an ongoing challenge with the atomic side of quantum. Do you see any other sticking points in manufacturability for some of the technologies you're looking at?
Yes. So I think we're in a really challenging position in general, in which we really need to have a large end market size to be able to drive the economies of scale that will allow us to support those larger markets. And until we can do that, we can't drive down the cost of a given quantum sensor. And so it's really, at least personally, it's not clear to me how we're going to, overcome that hurdle and, identify the right set of markets that will help us start to expand our manufacturing capabilities and drive down the costs of these devices. One of the big challenges that we're facing right now with Rydberg atom electric field sensors is just the laser systems. They're one of the two laser systems that you would use in kind of the standard configuration is just this big bulky thing that you're never going to get out of a lab, at least not easily. You could just barely touch your optical table and it could unlock, and so that's not something that's going to be really useful when you want to bring it out of the lab and use it in a realistic, communications or sensing application. And so I think that there is, a long road ahead in terms of figuring out the right pathways to work with industry, work with government to really, assess systems requirements for certain applications and identify the right pathways for supporting advancing laser systems to help them be more ruggedized, miniaturized, but still, of course, maintaining high power and narrow line width. We only ask for so much, right? And also in photonic integration. That's a really important capability, not only for Rydberg sensors, but also for atomic interferometers and other systems like that.
So there are different levels of availability of technical TLRs or whatever. So there's the very early stuff to the ready for prime time. And the focus at NIH is very end stage relative to DOE and NSF. So we usually defer to DOE and NSF for material science type things and construction. But one of the most important things to NIH is standardization. For delivery to a patient population, you have to be able to standardize. So early communication with NIST for this field is probably a very important thing, so that these kinds of things everyone doesn't reinvent the wheel, so that things can move forward. So the government spends a lot of money at the National Institute of Standards and Technology to standardize things. So people can get things in place with whatever they're doing, and they go in early with NIST. I don't speak for NIST, and I clearly speak for industry, but that to me seems like the most logical approach to use to try to save time and get things made fast. But it is going to be critical if you're going to do something in the human care, human health sector, that you can reproduce things and prove that you build the first one, you build the second one, you build the third one, they're all the same, or at least they can be tuned to be the same.
I think that's one of the challenges in picking up on what Bonnie said, right? Quantum sensing is dozens of technology platforms and modalities of choices of what you can use as the sensor, and it's hundreds of individual markets, right? There is no one quantum sensing market, right? It's inertial navigation, it's RF sensing, it's magnetometers, it's clocks, right? And each of those has a segment, and each of those has a set of requirements that kind of makes it challenging, right, to have kind of the one sensor to rule them all world, right? And I think we're in this world where we're trying to take pieces and put them into different market segments and apply them to certain problems, and some things are better than others in those segments, right? So I think we're going to live with that market for a long time in quantum sensing, and I think we're going to live with having to sort of figure out by technology choice the ways to get to the swap and the manufacturability for those technologies, right? I think that's going to be a big challenge over the next N years as we kind of commercialize these things into real volumes.
So maybe I'll ask Monty again, as the interface, at least on the U.S. side, between the government and private industry in many ways, where do you see the state of quantum sensing at the moment with respect to transferring all of this work where the center of mass is currently on the government side to private industry, and how do you see that interplay happening as the private markets start to take over in order to advance this technology?
Yeah, I think, well, it would be very helpful, I think, if we could have, increasing engagements with the private sector. I think one of the big, I think some of the biggest use cases of quantum sensors, in my mind, are for national security. And it's not yet clear how big the market sizes will be for the private sector. One, hope I always keep in the back of my head for, atom interferometer-based inertial sensors is, if we could only get the interest of the autonomous vehicle sector in these systems, I mean, that would give us the footing. That would really help us, drive R&D of these systems, and then we could leverage those advances for multiple applications, both for national security and for the private sector. But it's not clear that we'll ever really necessarily gain, a foothold in the autonomous vehicle sector, because it's not yet clear whether the long-term stability and accuracy that's offered by some of these atomic inertial sensor systems is really needed if they have, maybe a moderately good classical inertial sensor that they combine with, other, classical position fixing techniques like vision-aided navigation that might be sufficient for what they need. And so I think that's one of the biggest challenges that we're facing today, is to think about working to engage more with the private sector so that we can hopefully identify more promising markets that would allow us to sort of collaboratively develop some of these technologies for both private and defense applications.
So as the government person, go to quantum.gov for the mission statement, but the government is strongly trying to push everyone forward as a team. Just at the NIH level, there's a congressional mandate for 3% of the NIH budget going to the SBIR grants, which we mentioned, which have a quantum allowance. So 3% of $70 billion is being put out by the NIH for SBIR, and we allow in that space quantum stuff. So we are basically inviting as many people as possible to get involved with these $400,000, very high risk, high reward kind of things, early days type stuff. So that kind of thing is very important, and we in the government do our best to listen. What we care about is also workforce development, because there's nothing that's going to happen in the private sector unless the people that you need to do the work exist. So that's a major focus in the government. So we're trying, and I don't speak for the whole government, but I'm aware of conversations. The government's doing its best to try to get the people into the space so that you as companies have the capacity to do what you want to do and have the right people in the market so you can get things done.
I think one of the things we see when we engage with large customers or large potential partners or go-to-market partners is the first question is, show me your numbers, right? I have a classical system. There's a $21 billion market for inertial navigation today, right? So I have a classical system. Show me your numbers and show me that performance. Then the question is, well, what's your use case, right? What's your explicit use case and what numbers matter for that use case? And unless we find the best partners for those conversations in the commercial markets are ones who are interested in the research and development side of this, because if you try to jump to a product group that's going to productize a quantum sensor in some form or fashion of a product, they cannot consume it today, right? It's just too new and too different. And they need some research group, right? Like having worked at IBM, right? If you didn't have a product budget to do something, you're not going to be able to do it, right? So big companies have product budgets that fund product development. And so you have to find that research group that can consume the initial stage of that conversation and then get it on the radar of potentially embedding it into real products in those large customers, right? That's a real challenge for, I think, organizations to kind of work through that dance and do that fast and quick and get to some results quickly.
So maybe I'll ask, following up on that, where do you see the tipping point? So really small, nimble companies that kind of started out as SBIR companies or other small grants tend to be really focused on the research side. Very, very large companies tend to be narrowly focused on getting something in a product and actually achieving revenue. How can government and private industry help to get those technologies across the valley of death so that they have enough inertia to get to products, even though they've come from pretty hardcore research groups?
Oh, I think that's a question for Nick.
I actually like, there's a DoD Office of Strategic Capital chart that actually isn't one valley of death's not enough, it's 3 valleys of death. And I would posit that the first valley of death is idea to prototype. That requires a different kind of company. I think some of these SBIR and research fundings play into that. The second valley of death is turning that prototype into a product. And I think that requires a different company. And then the final valley of death is product to scale. And I think if you think of the problem in those dimensions, I think the right resources, the right funds, and the right teams, right? First phase is heavily research intense with a bit of engineering. Second phase is product development and engineering focused. Third phase starts to consider how you're really going to manufacture at scale, right? And I think that model really holds for this industry. And I think it's worth thinking about what you're doing as a company in quantum sensing or as a consumer of quantum sensing is trying to understand where that technology is. If you're trying to consume pre-prototype technology and you're putting it into a product, good luck.
Can I ask, where do you see the biggest deficit in companies today? Is it in that middle product or research to product part, or is it one of the other areas?
So we find, it's probably a similar experience, right? There's lots of good research funding from all governments, US government, DARPAs, DODs, Canadian governments fund a lot of that research. I think that transition to product development is hard, right? We see it, hey, we've done really good work with the Canadian Department of Defense, and they like the technology, but they have no way to translate into a real procurement process, right? And that's, I think, where the barrier lives for a lot of companies, is trying to go from, my prototype works, you guys love my prototype, now give me $10 million to buy a bunch of them, right? And I think that's a transition phase that needs help from streamlining, rapid adoption of viable prototypes into real end use cases in the government, right? We have a good program in Canada. I've talked about it before. Innovative solutions, government departments become the first customer of the prototype and testing partner. More programs like that, I think, make a huge difference for that translation of technology.
So really fast, there's a phase 3-ish kind of thing in the NCI or NIH where they try to give you funds to get through the valley of death. So we recently had a PET-driven linear accelerator product that is now a product to market. And people are coached along the way in the biomedical space. So as part of getting your funds, you have to have a meeting with the FDA. You have to have various things. And so people are encouraged and mentored along the way from people inside government with experience. That's it from me.
So Bonnie, any last thoughts on actually getting some of this technology to market?
Yeah, no, I think they said it well. I think, expanded, just continued open communication between government, industry, end users. That's really the key, and I think that's just something that we need to continue to work on improving in our field.
Any questions? Sorry, let me stand up. First off, thank you. Great discussion. Very valuable. We probably have time for just 1 or 2 questions from the group, if anyone has any questions for our panel.
Yeah, I just wanted to know more about that Canadian program and exactly how that works.
Sure. So it's called Innovative Solutions Canada, and they run a series of challenges and say, if you have a TRL-7 prototype, then they will offer a challenge. So there's been a bunch of quantum sensing ones. Usually the check size is $1 to $2 million for the purchase of that, and then they match that up with an end user department, right? So and the end user department doesn't fund it. The central pot funds it, and the end user department becomes, you build a statement of work and a testing plan, and the end user department kicks the tires on the technology, right? And then there's a pathway to purchasing, so that if you're an SME company, the government can buy up to $8 million of your product as a follow-on once it reaches TRL 9 and is ready as a product. So I'm encouraging if there's no Canadian government people here, I'm encouraging them to open it up to big companies as well. It would be great if that kind of project or program helped Canadian companies acquire our technology early and be sort of like that end user testing agency. It's just a commitment of time on their side, time and effort.
One final question over
Okay, I guess this would be directed at Jeff. I'm from Teledyne Corporation, so when I worked for small companies, the SBIR, STTR was fun, as actually Max and I did one together. As a large company like Teledyne, how can the NIH and funding agencies de-risk that big stage of taking it to an actual product, crossing that valley of death? For example, if we have to tape out a wafer and run stuff in the fab and manufacture it, that's $3 million of investment on our part in something that is high risk.
I don't have a good answer for you other than write a real grant. A regular big company can write a regular R01 grant, just like a university professor would. That would be the way to go. And while it's not $2 million, it's $500,000 a year in my institute, in my division, for 5 years. And a PO1 grant, things like that. It's not trivial. Also look at DOE and look at other government agencies that might have more flexibility with the larger companies. Also having small companies and offshoots and things like that, but make sure whatever you're doing is obviously legal.
I guess we'll end on keeping it all legal. Thank you, everybody.